All right. Two organizational comments. One is for those of you here after the presentations, don't go anywhere. We will have a reception with some food out there at 5. The second thing is that if you are attending SFN or you know people that are attending SFN, we are organizing a neuroimaging and data science social this year at SFN. It's on Tuesday, I believe, Tuesday night of SFN. So if you're planning to go to the Society for Neuroscience conference in San Diego in November, please come and say hi. And if in either way, please tell your friends to come and say hi. This is meant for NeuroHackademy participants, past and future, and friends and so on. So come and say hi. So those were the two things. And with that, we will continue with the presentations. On to Niv.
Thank you. Can you hear me well? Or you prefer with only the microphone? Okay. So hello everyone. My name is Niv Cohen, and this is my project presentation for NeuroHackademy 2025. I'll be sharing with you the tool that I built to streamline EEG analysis in BCI research. A little outline is the structure of the talk. I will start with the motivation. Why did I build the tool? Walk through the pipeline, the code, and show how the package is built. And we'll have a live demo at the end. And in one sentence, the goal is to make EEG beads pipeline much more easier to share, to use, and extend. So the motivation. The main objective and main idea was the project was solve a gap in the EEG pipeline approach. From my experience doing my thesis, I had a hard time to find a nice plug-and-play end-to-end pipeline that pre-process and visualize data. So I built this kind of a package that I just run from outside of this code. I don't care about the background and all the pre-processing stuff. I have a configuration file. And this configuration file can be good for two reasons. One, keep track on the analysis that I'm doing, and give a modular, efficient way of changing things from outside and not in each function that I need to do it hard coding. And from the user side, you just have, it's not just a bit actually hard, data in beads format, installing the package, and just run it from the main. You can see on the repo the name of the repository is BCI Viz, but I had a Eureka moment this morning. BCI, beads, BCI. So the name of the package is BeadsCI. And that one, I think it's touchable. We'll discuss about it later. It's a modular EEG package for pre-processing and visualization, built on MNE, which is a Python package for EEG. Structured by beads, and as I said, the thing that I want to accomplish is easy, flexible way of doing visualization and pre-processing.
You didn't share your screen.
Come again?
You didn't share your screen. We cannot see your presentation.
Like that? It is short?
I see it.
I can
Alright.
see the screen.
I see his screen.
I think whoever is that needs to switch to Zoom maybe.
I'm not sure, Khalil, can you
Okay,
switch
sorry.
to the other screen?
Sorry, I interrupted.
That's okay. Don't worry. So how does it look? From the code side that I'll show you next in the snippet code, very simple, loading data, pre-processing and plot the figures. And the user does not have to do that much installing the package that I'll maybe upload, have beads format data, and a configuration file in .yaml. So I'll walk through very fast. This is how the main looks. The configuration file, the manager, and dataset manager is the main class that I use with loading, pre-processing, and summarization with an option of enabling the plots or not. That's the method for the loading the data. What we can do is like we can run on subject, and on each subject we run in specific runs that I want and exclude. That you can configure in the YAML file. And this is where you can control if you want to plot something, to comment one of the plots that I show you the figures later in the demo, and some sanity checks. That's the YAML file. I didn't expand each one, but one for processing, one for visualization. Feature extraction can be added as well. You just need to change the root every time, or say the specific thing that you're doing in the task that you're doing, and how is the package structured, as I said, configuration, loading, some macro management of the data sets, preprocessing that's been called from the manager to folder name preprocessing. Specific, I didn't do that, I didn't show that because I focused on just one motor imagery task and not all of VCI tasks. So you can configure some task-specific logic in motor imagery, for example, some feature extraction there, and utils that can be used in all across folders. And we are up for a live demo. Are you ready? Woo! Let's hope. Let me show that. Doing full screen. Khalil, can you see the screen? I'm showing the second screen. Can you see this one? Okay. So you can see that one. I'm getting there. I'm pressing. So it will be 40 seconds. What I didn't do, sorry for that. Let me just get that one over here. There isn't a volunteer from the crowd that I want. No, maybe you. And just show you. What I'm gonna do, I'm gonna change here the name of the folder, so you'll get a new one. Noah Benson. Thank you, Noah, for participating. Second, the output directory. You can see there is no Noah Benson here. Over there. In a minute, there in a second, in a minute here, there will be. I will press the run button. The figures are gonna pop and close in a minute. And what I learned in this project was thinking of design, maybe, of how do I encounter or get into a problem, and on the solution. You can see now Benson up there now. Your results are very good. I see you signal SNR, a good one. And it's really fun. In this minute, I want to say as well to the NeuroHackademy project and organization. It's really been helpful and meaningful for me. Thank you for your patience. And I don't have a joke to tell you in the meantime, so we will wait another 20 seconds as I'm saving your run, Noah. Thank you very much. In the terminal, I can see all the, didn't show you that, though, but you could see some of the, sorry. Live demo. I think that you can look at it now. So now you have two subjects. Let's take this one. Each one has its own run that I configure in the config file. I can see the sensors that I used in your experiment. Second time, sorry. At the time, and as well as the computer is really slow. Sorry for that. A raw signal out of. Can't see that. So for the next, that one, and keep on doing that. This one as well, that I can show you, as well as power spectrum, if you want to see that, and nice figure, which is opening in my screen, and show it in yours. Thank you. With a nice montage, all kinds of features, all kinds of things that you want to show and present, can be modular and be changed. Some things about the epoch and each tile and each condition, and these things can be controlled outside of the code itself and just in the config file. So we'll change it for your screen. And to summarize things, it wasn't that easy or flexible because of the Zoom and sharing screen. I wanted something easy, flexible, and simple for doing EEG processing and visualization, something that I don't need to consider or be concerned about how it is going, what is being done in the back. I can change that. I can get in and add something that I want. I can just use the raw data and do pre-processing myself and get the visualization out of my package. No big setup for the user installing and having the bit format and configuration file, open source in your repo, for you to use that as well. And I want to say thank you very much. It wasn't that nervous that I thought it would be. Thank you again.
Good on that.
Yeah.
Configure.
Sure.
Right.
So pump extractor your own data.
What's up, Science Fam? We are the folks from NeuroHackademy, and so this week, the hack project we worked on was creating this Python package that can flexibly enable real-time processing for closed-loop fMRI experiments. So the problem that we faced, kind of similar to Nibs, was for me kind of a selfish problem, but kind of with the background at first. So neurofeedback is becoming increasingly popular in research today, both in basic science and translational research, as well as in clinical practice. So in this year alone, there's been a couple thousand papers using fMRI neurofeedback as a method in basic science research, and also this has been used in the clinic to help improve people with mental health ailments. And so this is kind of a typical setup for neurofeedback. So it's pretty complex. There's a lot of moving parts. So kind of typically, like when we're scanning, some little stick figure person's in the scanner there, and where normally the images would be acquired, sent to the MRI console, we pull them out after. There's some extra steps here where they're sent to some other computer that's doing this real-time processing, and then kind of whatever comes from that is sent to your experiment computer to update the experiment based on the feedback. And so to do this is requiring some kind of neurofeedback software to run this kind of processing in real time. So there's a couple of issues with the current state of neurofeedback software. First one is money. There are some packages out there that people use that cost thousands of dollars, and so this isn't super accessible for maybe most labs unless that is the thing that your lab does. Also, there's some other ones that are out there and that are good that are open access, but there are some other bottlenecks that come with it. So there's one out there that was started by a lab at Princeton, Ken Norman's lab, that uses a cloud-based analysis for this. And so there's some security issues here with having to have the scanner and the computer online at the same time. And I wanted to use this one in my lab, but they said it was going to take like a year to get all those permissions set up. So that's obviously not ideal to kind of executing these experiments. And the final one is non-flexible or replicable code that labs just kind of write and use for their own experiments. And that's where my kind of motivation came from. And that's what I was dealing with in my lab. Some grad student 10 years ago wrote some Python code that my advisor said would be plug and play, but I spent like 6 months trying to change it. And so ideally, a software that we can use for research is going to be open and accessible, flexible, and easy to implement. And so that brought us to our solution that we started tackling this week, which is NeuroHackademy.
Yes, so NeuroHackademy. The NeuroHackademy package, the goal is to decode brain activity from our fMRI volumes in real time. Our general pipeline is we're going to watch for diagrams coming in from the scanner, process those minimally with some minimal pre-processing, do some decoding analysis, and then display whatever is the result of that decoding analysis back to our experimental computer. One feature that we want to implement is some live web dashboard for experimental monitoring, just being able to see, oh, which DICOM I'm processing, what are the motion correction parameters that are happening, etc. So again, this is what we wanted to make. So our goal, still the same, decode brain activity for my volumes in real time, our pipeline, watch for DICOMs, process, decode, display. We also wanted it to be a modular script, so we're going to have separate scripts for our different key components. And again, implementing this web dashboard for experiment monitoring. So this is our general components overview. So we have this config watcher component that is going to load user preferences from a configuration.yml file. This is also going to watch and monitor for DICOMs coming in real time and trigger pre-processing and analysis events. The second module is our minimal pre-processing module, which is going to convert the PyGons to NIFI files, apply normalization to reference images and do motion correction, optionally standardize to MNI space if needed for your experiment, and masks the NIFI files to extract voxels necessary for whatever classifier you're going to use. The next module is, of course, our analysis module. So this, for us, specific usage is going to apply a pre-trained classifier model to our pre-processed NIFI volumes, and then predict brain states based off of the pattern classification. And then again, the dashboard, which we're really proud of, to allow experimenters to monitor and validate pre-processing. So the general structure of this package is going to look like this. With all of these various files that will go into a little bit more detail on what each does. Okay, so so the first is our backend and configuring the NeuroHackademy package. So the first step is the .yml configuration file, which is going to be our study level parameters. So these are things that will be the same from participant to participant in a study, but might change from study to study. What we're doing in order to actually implement this into the package is we've created two functions here. One, generating a configuration template that has all of the different parameters that we want NeuroHackademy to have access to, and then also validating that configuration template to make sure that if you set up a dashboard monitoring, that you actually have a dashboard URL in the parameters. The other thing that we wanted to do is make this package able to be run from the command line. So these command line arguments are going to be the session level parameters. So subject number, session number, whether you're doing debugging or not, etc. So we're using a Python package called parse to actually parse these command line flags. So we've created a various different flags that we thought were appropriate for this package. And the next thing that we wanted to do is have the watcher and pre-processing. So we're using a Python package called watchdog, which is very cool. It will allow you to monitor in real time files that are coming into a folder. So it's monitoring our DICOM folder. And these rolling events allow pre-processing real-time scans, DICOM by DICOM as applied. For each DICOM, we're applying this pre-processing pipeline. We're using DCM's mix to convert it from a DICOM to a NIFI file. We're applying motion correction, which depending on what motion correction allowed to use, it could be AFNI, it could be FSL, there's room to add more. Optionally, you can transform the image to MNI space, or if you need that for your classifier, and then also extracting the classifier ROI boxes. So one thing that's very cool about this is because these DICOMs are coming in multiple, like very quickly, you can process volumes in parallel with our multi-processing. So it will, once it starts processing a volume, it can process the next one without stopping.
Cool. Okay, so once all that's done, then we get to the pattern classification. So this part is something that needs to be configured that for each experiment, the experiment will load in is some pre-trained scikit-learn classifier that's saved out as like a pickled object file. This is also nice too. The original version of this that I was using for my lab was in Python 2, which was gross and old. And so now, it's Python 3, sklearn that everyone uses. So you load in this pre-trained classifier for your experiment. And then as this kind of as the processing is going throughout a trial, it's taking recent TRs that are being averaged together and then the classifier is applied there. And one of the things that can be said And the configuration file is basically how many TRs is in that sliding window. So you can configure that at the beginning. And right now we have it set up to do a couple different types of classification. You can get just kind of like a single label of what class it thinks it is, class probabilities, or this kind of custom function I built in. It's like neural evidence. So from 0 to 1, the confidence from the classifier for each of those classes. And so once this is done, it sends the output to a couple different places. It will send it via post request to your experiment computer with a URL that you send the configuration file, and that can be used with coding your experiment to update whatever visual display. And then it's also being sent to this dashboard that we built. So I won't go into too much how the dashboard is working via code, but like Deepa said, that there are arguments you can put in the configuration file if you want to use this or not. Basically, it looks really nice like this, where this is not like a GUI thing the participants are seeing, but because all these volumes are coming in really fast, they're being processed in parallel. Looking at the terminal doesn't really tell you anything about what's happening. So that this can be open on the experimenter end to kind of monitor the process as it's going trial by trial and show you all the kind of high-level parameters that you want to know. And so right now, the package kind of works. We built it, we were able to hit install it. That's cool locally. And let's see what else do we have here. We were able to run some of the functions independently from here. Things like generating the configuration file worked across all of our laptops, so that's cool. Yeah. Okay. So wrapping things up. So 4 days is a lot to work on this, and there's a lot of things that can go into it, but I think a lot of the kind of modules are working. So next step would be to kind of validate the full pipeline from start to finish with some kind of test data, adding some different supports for smoother, I guess, updates and sending information between systems, just general optimization for making the real-time processing as fast as it can be, including other MRI feedback options. So maybe like univariate activation or functional connectivity, and also building this out to be capable to do neurofeedback with other imaging modalities like EEG, MEG, stuff like that. And so this has been a great couple weeks for me. And I think I've learned a lot. Collaboration, I'm not too scared of GitHub anymore. Lean coding, modularization, some beginner software development, and using LLMs to help write some files for you that you don't want to spend the time writing. And so that, thank you.
Also want to shout out our other team members, Lynn, Hilda, and Mika, who aren't here physically right now. But constant.
So Punk's extractor, you're up, and on deck is on deck is dicompatibilities.
Okay, hi, I'm Jamie and this is John, and we did what was called Construct Extractor about an hour ago, but then ChatGPT gave us some good ideas for some cooler names, so now we're Cortex Extractor. So the goal of this, first I'd like to thank all the contributing members of this team. Svenja, who is a remote attendee and in a very, very poor time zone to meet at 4 o'clock in the afternoon, is probably asleep right now. So she will not be joining the presentation, but she also contributed a lot. So I just wanted to point that out. And then John and myself also were the in-person members. So the goal of our project was kind of actually inspired by a previous iteration of a NeuroHackademy package that was created as a hack project. Shout out to Mackenzie, who was a part of that team. But this previous package called F-sub-extractor used functional labels to extract subcomponents of white matter bundles and measure things like structural profile analyses of individual functional regions. So I really liked this idea and I wanted to run with this idea, but kind of extend this functionality to be a lot more flexible, be able to take in labels of any type of shape or template space, and be able to segment information from various types of structural scans, not just from white matter tract profiles. And so the goal is kind of to use this model as exactly that, a model to design what will be a very, very flexible package slash like hopefully ideally eventually a single function. Spoiler alert, it is not a single function at this point. But how the goals that we had for kind of this hack week, not all were accomplished. The first, we wanted to be able to adapt the code to use any sort of ROI. So that means a volumetric label or surface label from FreeSurfer, anything could be an input. It would automatically take that label and transform it into the correct space that is needed to project it onto whatever structural scan or structural image you're working with. So we could extract things from several modalities. Another side project that kind of materialized from this project was just realizing that there aren't very many scans that combine things like diffusion and quantitative T1s or quantitative structural scans and functional data. So also just figuring out ways to kind of compute our own test measures. So that was another little side project. And then finally, the end goal is to make this easily extensible package that again can be flexibly used and applied to many circumstances. The timeline of how we were working Monday, we really didn't do much besides getting our GitHub set up because I believe all of us were brand new to GitHub really. So that was a lot of fun. And so we figured out the data sets we wanted to use. We figured out GitHub. Tuesday and Wednesday, we were kind of just figuring out like what actually needs to be done, understanding what goes into making a package. And throughout the whole time, we were kind of coding and attempting to complete this large undertaking, which was a package. So to get started, the first thing we realized we needed to do was figure out how to project labels and ROIs into different spaces. So we wanted to create, like I said, any possible transformations. So that's surface to volume, volume to surface, template to native, native to template, back and forth as many times as you need. To get started with that, we ended up making a bunch of utility functions that do one-way conversions. So we have functions that are highly supported by NeuroPython, thank you, Noah, that convert from volumetric space into surface space and back and forth. So as we can see here, we're actually using the Sitesman 300 Atlas, the first ROI. Thank you, Jake, for providing that. So this was a label that was in volumetric space in an M&I template, and we were able to actually transform it into the native. Well, this actually is a picture of FS average, if you're familiar with FS average, but we were also able to transform it into FS native space of our first subject from the NSD data set as our test case. And we were able to do the reverse as well, where we go from FS native all the way to an M&I label. We were also able to do within surface or within volumetric transformation. So here we're looking at an example of a within surface transformation where we take an FS average V1 ROI and project it into the native space of two of the individuals from the NSD data set. The good news here is what you can't tell is there's actually two labels projected onto each of these participants. It's just they're the exact same because the one label is actually the FreeSurfer generated V1, whereas the other one is the NeuroPython generated transformation from FS average to FS native. And they perfectly align. So that was really happy. That made us one, very pleased with Noah's code that it works very well for interpolating and transforming ROIs from one space to another. And then I think John will talk about the rest of them.
Hello. So part of the flexibility that Jamie talked about is being able to transform between volumetric spaces. So for example, transforming volumetric M&I ROIs into the native volumetric regions for the scan. So basically this takes the M&I space ROIs and it transforms them using affine registration first, which is the linear transformation, and then the symmetric normalization after that in order to do the non-linear transformations. And then you apply those transformations that you calculate in order to get the ROIs from the M&I space to the native space for the subject. And here's an example using some M&I space ROIs that we found openly available. and it transforms them into the native space. And without being intimately knowledgeable of the ROI specifically, it, overlaps the brain. And of course, the registration isn't going to be perfect, but you can always tweak it, and we provide the flexibility for that. And in going the opposite way, so it's basically just the inverse transformation. So going from the native space ROIs into the M&I space. So for that, you basically just have to provide the M&I template, which gives the structural space to project into, and you do the exact same calculations, just going from the native space ROIs into the M&I space ROIs. And here's another example of that using the NSD data set. So using their general ROIs, which is basically the white being just cortex and the red being the ROIs in question, it's able to transform those into the M&I space. And another bit of flexibility that we added is brain masking. So you don't have to provide the skull stripped T1 scans. It will do the skull stripping for you. But of course, for your own data, it would have to, be tweaked based on the registration.
Okay, so for next steps, one of the things we didn't talk about was the actual extraction of the structural data. That is unfortunately something we did not get to during this past week, but it is something we want to continue to explore to be able to use this package to finish the rest of the goal, essentially. We were really excited. We were able to get one single parent function where you just have to do a few parameters of input, the label itself, the free circuit folder for the individual, their T1 if you're even using a volumetric ROI at any point, and then just the indicators of what your starting region is in and what your ending region is in, and it is able to spit out a label that is completely transformed in the space that you want. So we have the first half of our very flexible package down. We still have a lot to go. We also admittedly did not test this on very many test cases. So we do want to make sure that this works not just within the one small data set of 8 participants that we use, but that it actually is consistent and works with data from multiple labs. We also want to, again, create this as a package. So we want to go through the whole writing of like init files and TOML files so that we can actually create the online package aspect and take it away from the module space that it currently lives in. And then finally, another thing that I actually just added a couple minutes ago, because I realized after listening to Neve's presentation that bids is something that a lot of us work with. So I think another thing that could be really cool is to just kind of create this as more of like a bids package that can automatically do these things if you point a list of labels and a bids directory to the function, that it would be able to just automatically generate these based on the files that you have available in your NAT folders. So just a lot of ideas about how to create this to be a more flexible and more automatic package are kind of like still filtering through our brains, I think. And with that, thank you to all of the instructors who have helped us both a lot over the past few days, and to all the neurohackers who have also helped us mentally and emotionally. And for ChatGPT.
Like on the move to go out and Local Connection, you were on that.
Can everybody see my screen okay?
Yeah, we can see you.
Okay. Okay, so my project is creating a tool that can help analyze DICOM headers and use large language model or LLM to help with their DICOM to bits conversion. So we all know about bits by now, so because bits is a standardized way to organize and describe data, so it make it very easy for you to for people to share data to one another because everybody understands their data organization right away. And if there's like a data type that requires certain DICOM metadata to be saved in the JSON sidecar, then it's very easy to check. Another benefit, if your data is in bits, is that you can use many bits apps, which are very easy to use, and they're all containerized, and they ship with all of the dependencies that are required to run the software, so it's very reproducible. Some kind of downside of using starting to adopt bits is there's some learning curve. There's lots of very good documentation for bit specs and the bit schema. The more the more difficult part is kind of their mapping between DICOM to bits. There's a lot of software existing that can help with the conversion, like HUDICONF or DCM to bits, but those programs require some kind of like mapping that is like that is user inputted so that the program can do the conversion. So you can imagine, and this is also the motivation of why I want to do this, is if you have a very large data set that is very heterogeneous. So let's say it's not as clean as research grade data, but you have a lot of data coming from like a hospital with a lot of different sequences for the same MR modality. Then kind of like this process of mapping from DICOM to bits that requires user input can be very consuming, time consuming. And I have this example from HUDICON, and I kind of like want to start with HUDICON because it's part of their NiPi ecosystem. But this is an example of the mapping. So with here you have the create key function that essentially you put exactly their the pattern of the bits file name for each of those data types. And then here is where kind of like the mappings happen. So you have different DICOM metadata, and you create conditions for those metadata that if those conditions met, then it is part of like one of the like sequence that you want to do the conversion on. So an example here is for T1. So if the dimension 3 is this number, if dimension 4 is 1, and if T1 weighted is part of the protocol name, then it's going to be that sequence is going to be appended to this list. So essentially, this is the part where like you need to do their mapping from DICOM information to then convert it to bits. So again, if you have lots of data with very heterogeneous sequences of, let's say, the same data type like T1, then this like you have to write a condition for each of them. So this project is essentially trying to see if we can utilize LLM because we have like everything is text-based. So you have the text-based DICOM information from the header. And then with bits, we have bit schemas. So essentially like this, the objects is kind of like the vocabulary of what bits is. So like you have the different like entities, so like subject, session, task, are entities, and then you have surfaces. So bool, T1, DWIs are their surfaces, and then you have the data type, which is the inat, func, and DWI. And you have way more, but those are just some example. And then you have the rules of how those kind of like vocabularies can interact with one another. There's a lot of rules, but this is just an example of this is how bits expect all of their entity, like the order of the entity needs to be exactly this way. Otherwise, it's gonna be not like a not bits validated. So for the, I'm just gonna stop sharing screen for a moment because the rest of it is just gonna be demoing what I'm trying to develop. Whoops. Okay, there we go. So I actually have not cut a release of this because this is still very much in development mode. But it is on Docker Hub. If you want to test it out, you can by pulling from this tag. So there's like so I'm just gonna go through a workflow of this software. So the first thing that you need to do is you need to grab all of their DICOM's headers that are important to kind of grouping and kind of classifying your sequence. And this function actually is just a wrapper of running HUDICON with no conversion because it's gonna output DICOM information for you. So like you don't have to run it through this. You can just run HUDICON directly. But this function is there, and it allow in case you have a lot of data and you want like let's say each of their session to be a different task array. I do have an argument where it will produce kind of like a template for a job submission of running all of their sequences in your DICOM input directory. And then for the group sequences, this is an example. This is just a concatenated of DICOM information that you're gonna get from running HUDICON. And then this is the grouped one. So you have like how many sequences is part of the group. And then you have other things that is required to like create the conditions to do the mapping from DICOM to bits. So we have protocol name, series description, sequence name, dimension 1, 2, 3, TRTE, is derived, is motion corrected, image type. And so my hope was like, so like this sequence, it has kind of like the most, this group has the most number of sequence. So this is kind of like the main thing that we want to do a conversion. And then we have kind of the variant of that. And basically the two rows are exactly the same. The only thing that's differ is DIM4. So essentially something happened, I guess, during this scan, such that the scan time is just shorter than the kind of dominant group. But that is like something that is important because let's say if you only care about resting state with like a full duration, then you want to like set DIM4 as one of the conditions to do the conversion and just skip anything that doesn't have like a particular amount of scan time. Okay, so that's grouping. And then the next part is the mapping, which is using LLM. So I'm using Llama, which is from Meta. and they share this openly on Hugging Face, and you can download it. So they share their 8 billions parameters and the 70 billions parameter. With testing, I'm just using their 8 billions one because it's much faster to run. But it's with with this function, essentially, it's like you're writing, it's very similar to how you write a prompt to ChatGPT and it's output the answer for you. My prompt is all of the um, DICOM group information and all of the bit schema, and I ask it to do the mapping for me. And this is an example of what a prompt look like. So this is from the bit schema. There's a lot of them. There's a different MRI data type and surfaces. I'm just gonna try to skip through this part because there's a lot of them. And then we have the entity order. Again, this is important in constructing that file name. And then I have the task for the model, which is mapping the DICOM series group to the appropriate bits data type surface and entity. And then I have some constraint. And then I also have an option for any additional context that the user want to use. So like, for example, you can add that you only want to use the motion corrected for funk, for example. And then I also give the model, this is like an example output that I want from it with all of this information that is needed to create their bits file name. Oh yeah, and this is the additional context that I mentioned. So that's the prompt that is being entered into their the model, and this is the output of that. And this is just testing with the 8 billion parameters one. So this is the same data frame. Those are the things that were added. So those are their kind of their proposed bits path that that llama is suggested to me, and it also gives me this bits confidence. So the one that they are very confident in is the easiest one, where everything is already included in the protocol name. So so it has the correct data type, the correct entity, and then the correct service. And then here is where things kind of went downhill, where it's not confident in. So this is QSM. And so if you go to the bit schema, it's this chi map. But the model was just very confused. So this is what it thought to be the surface. There's no GRE. So there's a lot of like issues where it's where it is when the task is more difficult is where this kind of like start falling apart. There's a lot of improvement to be made on this. But once you are done with the mapping, then the next part, uh, um, um,
Yeah,
sorry.
you're at almost
It's
15
time?
minutes already, so we need you to hurry
Okay,
up.
yeah. Okay, sorry
Yeah.
about that.
Oh, if you have a conclusion, go ahead.
No, I just want to say thank you to the organizer of NeuroHackademy. The last 2 weeks has been a blast. So yeah.
Thanks.
Hey, we have funky connection, I think. Yeah. And HCP protocol verification, you're on that.
I've actually used them.
Okay, so we are Funky Connection. And basically the objective of our project was to identify differences between healthy and depressed brains, and then to test differences in those network metrics between those brains, and then also to use the functional connectivity data of both populations to see if we can predict the level of depression using a graph neural network. And just one note, Daniel's not able to be here today because it's like 3 a.m. in India, but he did contribute quite a bit as well. So this was our day one GitHub workflow. It's a little incoherent, so not much to say, but just wanted to say that it was extremely helpful having all the Git lessons to help us organize and streamline.
We're done. So we used the transdiagnostic connectome project mainly because it contained behavioral, clinical, and MRI data, and this allowed us to explore brain connectivity through psychopathology. Okay, so about a bit about this data set. It had 241 participants. About 60% of that was patients, and about 40% of that was healthy controls for the general population. The age range was 18 to 70 years old, and it collected anatomical MRI data and functional MRI data, with which we focused on the resting state data. Additionally, we used the cognitive and questionnaires as well as clinical interviews. And then finally, you might be wondering why we chose such a small data set. This is because it offered pre-processed data, and that allowed us to hopefully explore the network connections better.
So as Samantha says, pretty much we use the process data using the minimal processing step, which is usually the global signal regression and the parcellation from the Schaefer atlas using the 400 regions. And basically, something that we wanted to make sure is that we also control the analysis for motion. So we calculated the interface displacement for each of the 4 rounds and actually averaged those. For each participant, which means that we have at the end 13 participants that needed to be removed because of high motion, using the typical threshold of 0.2 millimeters. And later, because we wanted to do something that Diego is going to talk about in a second, we needed to kind of like filter by phenotype, so all the participants that have completed certain questionnaires. So at the end, we end up with 175 participants for analysis.
So we were interested in anxiety and depression. These two disorders are highly comorbid, and we were interested in whether we could find functional connectivity correlates to these two disorders. And in this data set, they acquired a lot of data from different questionnaires that all of them measure different aspects of depression and anxiety. So we wanted to merge all that data into a single score, and we did that with principal component analysis. You can see that in the first column of this heat map that a lot of the questionnaires are loaded into the first principal component. And on the right, you can see that the values of the subject values of this first principal component are higher on the patients than in the subjects from the general population. It is worth mentioning that the patients are not necessarily depressed, all of them, or with anxiety. They could have other disorders, or maybe they don't even have depression or anxiety. Next slide, please. So one of the first approaches that we tried was correlating with traditional statistics, the mean within network functional connectivity to the first principal component of depression and anxiety. And we did that with a linear mixed model where we also control for other demographic variables such as sex, age, motion, and the site where the data was acquired. We did this for all of the 17 geo networks, and we did FDR correction. And as you can see in the plots in the left, there's no significant association of the functional connectivity of the within network or within functional connectivity of these networks to the first principal component of the anxiety and depression. The second approach that we tried was performing, because there's not a lot of data, there's only like almost 200 subjects, we decided on using penalized regression, laser regression, between the 400 nodes from the Schaefer Atlas and their degree and the first principal component. And the result is that basically the best model is still has a narrow square of 0. So basically we are not able to predict depression and anxiety based on the node degree. So we were kind of worried that maybe we were doing something wrong. So we wanted to do some sanity check, see if we could predict age from the node degree. And because that's probably the one of the phenotypes that it's easier to predict compared to behavioral phenotypes. And we did the same strategy, laser regression with a split test and validate and test training and test without k-folding. And we got the best model with the optimal alpha value, the penalization value was 0.43. So we are actually doing this is actually doing a decent job at predicting age. And there's only 30 nodes that do so. And you can see them above in this plot. Yeah, next.
So in addition to that analysis, we were interested in calculating network metrics for both populations to see if we could characterize differences between depressed populations and general populations using these metrics. So we were interested in global efficiency and nodal degree for each parcel. And like Andrea mentioned, we're using the Schaefer parcellations, there are 400 parcellations. So the variables here that we were interested in was functional connectivity as our independent variable, and the categorical outcome, which was included in the data set, was whether the participant was part of the depressed cohort or from the general population. And I'll have more to say on that in just a moment. But just a side note that this is created using NiLearn, so that was another side of learning for me. So these are the results. So first is looking at node index. You can see on the x-axis is the index of each parcellation of the brain. And on the y-axis is the negative base log 10 of the FDR corrected p-values. And the blue horizontal line would be the significance threshold. So none cross significance across any parcel in the brain, meaning that there's no statistically significant difference between general population and depressed people in the sample using the functional connectivity matrix. So a little disappointing. We were hoping there would be something, but nothing here on the node difference or node degree. Looking at global efficiency, it's this lower left-hand one, same sort of thing. You can kind of see immediately the means are basically identical, and there's no statistical difference in global efficiency between these two populations. So this led us to think like, what if this outcome measure that we're using is actually not capturing depression because it's general population and depression, but general population people could be depressed. We don't know exactly how they're categorizing them. So maybe this is just the variance isn't in the outcome variable. So we decided to use the principal component that Diego had just talked about that was based on a whole bunch of metrics that were aimed at capturing the variance in depression. And we're hoping if we use that as our continuous outcome variable and we regress on it, maybe that would actually show a statistically significant difference. And it doesn't. So it's a mean of 0. There's no difference, no relationship between global efficiency and the symptoms.
Hello, I am back with more GNN stuff. So, at the time, well, we didn't know we wouldn't have any results, so we decided, maybe we can try other difference models and see if we can predict these depression scales. So the objectives of this was comparing against the traditional statistical methods and then investigating pre-training methods. Now, why is this? I didn't mention this in my talk last time, but these kind of models are actually very data hungry. So the GNNs I work with are normally trained on like at least 1,000 participants, and this is a data set where I had 150 participants. So it's definitely a challenge, but we were up for the challenge. So just kind of like model specifics, in this case, we're looking at graphs where the features were constructed using graph theory metrics, because we only had the functional data. So we were looking at low degree, clustering coefficient, these kind of metrics. And then our edges were based on functional connectivity, and we can also train the threshold to, for example, retain only like 20% of like the top connections. In terms of the actual architecture, we're looking at a graph retention network with 2 layers, so that I optimized everything using weights and biases. And the way we do this is with Bayesian optimization, which means that the hyperparameter search is informed by previous runs. So it's basically trying to find like the best parameters to optimize this. So in terms of atlas comparisons, so at first we started with 400 regions, which is what the data originally was. And given we only had 150 participants, this is kind of the dimensionality issues that you get. So we did took an executive decision, which I don't endorse in general, but we decided to instead focus only on the default mode network because we know this is associated with depression and anxiety. Initially, we wouldn't do this. We want the model to specifically pick up on this network, but this was just decision made to make life a little bit easier. So that you can definitely see that across, my pointer is there. You can see kind of like the comparison of the loss curves, the R squared and the R, they definitely become a lot smoother when we use less data. So this at least helped for this week. In terms of the pre-training results, so why do we do pre-training? So the idea is that when we have very small data sets, that we are quite limited on the available labeled data, we can carry out these self-supervised tasks. So the idea is that the model, before doing like the main task, can learn kind of generalize the practice. And it can help.
Okay, so quickly the conclusions are that we pretty much collaborated this indeed. We were debating if we have learned or learned. Well, we use all the learning from the NeuroHackademy, so pretty much now we will talk about it, use a couple of packages like Niner, Compile, Canvas, and so on, and we perform a number of analyses of PCA or theory measures and with comparisons and so on. And Diego pretty much made the point that we, even that we didn't get any significance, we actually make a significant friendship out of it.
Right, you see people global communication, and it's, I think, fairy tales on that.
Okay, so we are Muriel and Adrian. We work together and with the help of Lee, who is online. And we work on the HTTP data and the regional data set, and we try to compute the cortical magnification. So first, you may ask yourself, what is the cortical magnification? And the answer is that it refers to the proportion of the visual field processed by a specific area of the brain. So if I take the visual field, I can say that this tiny portion of the central visual field is the forehead, and all the rest is the periphery. But now, if I look into the brain, by example, in Q1, the first visual area, what I will see is that most of the brain is occupied by dealing with the fovea, and the rest is the periphery. So there is another over-representation of the fovea in the brain. And these have been studied in MRI, by example, in different papers, and one of these papers is the Ari and colleague paper, where they show that there is a sharply decrease of the cortical magnification with the eccentricity following this relation. And also there is another paper which we use as a ground truth, which is the open paper, and And it gives us this relationship between the cortical magnification and the eccentricity and how it's supposed to decrease. And then we need to know, okay, it's good, but how can we compute this cortical magnification with fMRI data? So for that, we use surface-based MRI, and like I told you before in my first talk, we can model the PRF parameter. And if you imagine this being a visual area as V1, by example, we can take a vertex, which is this blue point here, and we can have its corresponding population receptive field. And now if I take a circle around this vertex, like 5 millimeter, let's say, I can take all the neighbors. Here I represent only 2 of the neighbors, but you have to imagine that here, everything is a neighbor. And I can have the neighbors and I can have their corresponding receptive field also. And then what we can do is measure the geodesic distance of the neighbors with the vertex with all of his neighbors and take the median. And we can do exactly the same with the visual distance on the corresponding receptive field. And finally, we obtain the cortical magnification in millimeter per dBA, which is just the division of the geodesic distance with the visual distance. And now,
okay, so basically for this project, we wanted to take this method that Uriel just described, and we wanted to apply it to the human connectome project data, specifically the retinopathy data that they had, and to see if this method would work on a pretty large retinopathy data set. So just a little bit of overview of this data. So this is 70 MRI data with 181 subjects, and each of them did 2 runs of retinopathy fMRI, and so that's what we're drawing from. Just to give you an idea of what one subject's data looks like, this is the first subject, and you'll see on the graph that the colored lines represent V1, V2, and V3 respectively, and then the black line is the Horton model, which we use as the ground truth. And there are the R squares there as well. And you'll see that actually all 3 regions fit that ground truth line quite well. But obviously this is just one subject's data, so we want to look at all of them. And so we generated a graph of across all the subjects. Just to note here that the previous graph we didn't bin the data. We wanted maybe a truer representation of the fit of the model. But here, just because the data is a different shape and different size across different subjects, so we binned it to give a sort of I guess a fair representation across subjects. And so as you see here, the shadow represents the middle 50th percentile, so 25th and 75th percentile of the data. And then the model fit again is the colored line, and then the black line is the Horton line. And again, you'll see that it actually fits quite well across all 3 of these regions. And just a shout out to Noah, because V1, V2, and V3 were defined using the NeuroHackademy hand-drawn sort of annotations there. Okay. And so finally, the last step we did was actually extend our results beyond early visual cortex. And we did this according to the Wang and Cassner atlas. It's an anatomical atlas, and we basically applied that to the HCP data. And then a couple of things to note here, I think. As you'll see, compared to the previous graph, these colored curves also fit the Horton model quite well in early visual cortex. Another thing to note is that Here for the Lancaster atlas, they also split early visual cortex into ventral and dorsal sections, which gives slightly different cortical magnifications. But overall, the curves still fit the ground truth quite well. Moving on to higher order visual areas, you'll notice that these curves are quite a bit flatter than the early visual area curves. And this is true for these other sections as well. We think the reasons for that are several. One is that as you go to higher order visual areas, the PRM size increases, and so the overlap in that sort of cancels out the effect of the phobia having more representation in cortex. There are a couple of things as well. So yeah, these are our results. And just to reiterate, we found that cortical magnification sharply decreases as eccentricity increases. We saw that the magnification data fit quite well in early visual areas to the Harvey equation, as well as the Hilton equation. But this fit was less well in higher order visual areas. I think the main takeaway is that this method of computing cortical magnification is relatively computationally light, and it also gives results that we actually expected and that are in line with several previous investigations. So future directions here, just to wrap up, we had considered calculating the cortical magnification using geodesic area instead of distance, because the area would give like a truer representation of sort of magnification of the translation from like like the retina visual area to the cortical area. But we didn't really have time for that. And then Noah also suggested we investigate the difference in magnification between horizontal versus vertical meridians. Again, didn't have time for that, sorry. And several other directions that we could go in. We could investigate whether the changing of the size of area around each vertex, whether that would actually impact the results in any significant way. And then sort of looking at differences between methods of calculation and visual differences as well. There's several directions so that we could go in. So that's it. Thank you to Jacqueline Lee, first of all, for her contributions in our early discussions. And then thank you to Noah for your help, and then the other NeuroHackademy organizers as well for organizing this event. So thank you.
So next is fairy tale. And on deck is narrative event boundaries.
No. I think we can just share.
Okay, hello, everyone. Thank you. So our team wants to present our project called Fairy Tale. The project slogan is "Give your data a happily ever after." Yeah. Okay, so first, just a question. Who in here does not know about open science? And I don't want to see any hands raised. Perfect. Click.
Nothing's happening. Okay. So open science, what is the sorcery? Replication crisis, we all know about it. The symptoms of it has been low reproducibility rates, selective reporting and p-hacking, publication bias, and a whole lot more. We know about this. And this has resulted in the need of openly accessible scripts, data, and the analysis from published experiments. So to publish open science. There's also online repositories like OSF and Zenodo, which can publicly publish your information on from these experiments, and also the need of pre-registrations that includes what is to be studied, how, the method, and the expected results, and so on. But also guiding conventions on how to make data accessible, readable, reproducible, and understandable. One problem with open science, according to me at least, is that it is immensely time consuming. So to publish open science, it takes a lot of time to organize all your stuff, basically. And this can also result in unstructured repositories, which you then upload into an OSF or Zenodo or anything else. There's also a problem of missing information to allow for replication and reproducibility. And there are researchers who do not follow the guidelines that have been proposed. This is an example of an OSF repository that I found, and this is actually from a prominent researcher. Okay, I don't know if you know this. Sorry. And this researcher actually works with open science. But I thought that this was a bit uninformative, and everything is in text files. I don't know what I'm looking at. And some solution to this data sharing, is the FAIR guiding principles, which are F, findable, A, accessible, I, interoperable, and R, reusable. You can read about them in this very dry article if you want to know more about them. So what is the solution to all of this time-consumingly open science? Fairy tale. Okay, I'm going to try to read it. FAIR archive infrastructure for research. It's your template for accessible and linked evidence. Thank you, ChatGPT. So what Fairytale does is it creates a local repository on your computer. You can access it. These guys will tell you more about it later, but you can access it, upload files with necessary information such as the data, the scripts, the results, and the metadata. And then you can check and verify if the repository includes everything that you need and everything that is, what we think should be in it. And then you can easily upload this local repository to to an online repository such as OSF, Zenodo, etc. And the developers.
So the first thing we had to do here was kind of develop a standardized structure for sharing a repository. One thing to note and to distinguish this from bids, which has been talked about a lot, is that this fairy tale kind of pipeline is supposed to exist above just the data set level, but kind of be a little bit more encompassing of an entire project. So we're all grad students, we have a bunch of different projects we're working on, constantly creating all these folders in our computers that we're populating with different things. If you're like me, by the end, it's just a complete mess that I don't want to look at, and I spend like weeks just trying to organize everything, individual files, directories. We came up with this structure that has some recommended directories and file types within the directories and subdirectories, and some more optional subdirectories that we kind of give as recommendations. At first, we developed a terminal-based tool, but we thought it'd be more accessible to move towards a website, which we can kind of do a little live demo here. So this is our fairy tale pipeline. There's two branches. The first one is a kind of creation workflow where you can kind of create something from the bottom up. You can name something like your project just test, and it'll create the folders, the subdirectories in the overarching folders. But if, for example, you may have already started data acquisition or created a consent form and like, you know, have different documents, or maybe even finish the project, you can also upload your files directly, just drag and drop or choose them, what have you. You can add your data, you can add your scripts, results, metadata. But if you don't have anything, you can just download the actual project and it'll give you a bit of a skeleton repository that conforms to our guidelines. These are all empty, of course, in this case. We also give you a template for what a README should look like. That's informative for your registrations, things like that. The other half is a validation tool. So maybe your lab already has kind of a way of doing things, and you just want to check to see if it adheres to FAIR principles. You can choose your project and zip it. Here we have an example of that repo that was previously talked about, and you can just run the validation on it, and it'll give you like a bunch of passes and checks, some warnings. It'll tell you what's wrong, why you might need something, recommendations, why we recommend it, and a reminder of like, yeah, different types of things that we feel are important. You can also generate the report, download it, and I don't know, do whatever you want with that, I guess. It kind of gives you like a nice little content. Thank you.
Thank you.
Okay, there's the bet boundaries. Good. And on deck is diffusion, arrivation, and development stage.
Hi, everyone. Our project, well, I'm Natalie.
I'm Ben.
Ben. And our project is titled Mapping Brain State Dynamics to Narrative Event Boundaries. Fun little data analysis project, lots of pretty plots. Yeah. Our research question is, are LLM decoded event boundaries represented in the brain state dynamics during narrative processing? So the data sets that we were working with was this Nastase narrative data set for the brain data, and it's like 300-ish people that listen to stories during fMRI acquisition, and we used a subset of those people, like about 75, that watched or that listened to a story called Pie Man. And yeah.
Yeah, and we also use LLM derived event boundaries. They also compared those to kind of human consensus event boundaries and found that the LLM derived event boundaries for the narrative were very similar. So we went ahead and used the LLM derived boundaries because they basically, like, people vary a lot in where they demarcate boundaries in a story, whereas an LLM won't. But it kind of represents some sort of consensus among human interpretations. And so yeah.
Yeah, and we have a little excerpt down there from Pie Man that you can read at your own discretion. But yeah, fun little Ralph Moth radio hour story. You can go listen to it in your free time. Yeah, so our analysis plan, just to lay out kind of the structure, is first we wanted to extract states from the fMRI volatilized time series data. So to do that, we kind of just collected all the data that we would need from the story, did some like light pre-processing, and then we extracted the network level signals as a dimension reduction step. We use these like 14 canonical brain networks from the Shire paper.
And then in order to actually get states from that, we fed hidden Markov models to that, which we'll talk about in a second. But yeah, we went through some model selection steps with the HMM. And then after that, it basically spits out state paths and brain state transitions, which we'll also get into in a second. But yeah.
And we took those LLM boundaries and we just kind of binarized them, which then allowed us to get to what we did for most of our time, which is we actually doing it.
Yeah, we basically were just testing if they correspond. So if these event boundaries in the text, decoded from an LLM, correspond to state dynamics and the brain activity. So yeah, we did a few tests, which we'll get into, but. Yeah, so just introducing the concept of identifying whole brain states. You can do this by, you have your voxelized time series, so you have this regional bold activity. You can either do it like parcellated into ROIs or like network level signals, and you have this for each subject session, whatever. And then you can there are a few different approaches. We chose hidden Markov model because it kind of takes into account the temporal sequence of these patterns. But you can also do stuff like K-means clustering, tensor decomposition, stuff like that. But the hidden Markov model basically identifies recurring states of collectivation and the brain activity. So that's what we used, and it spits out these state paths or Viterbi paths, and you get kind of this one-dimensional vector of states over time. So it identifies like what is the most probable state that this brain activity is reflecting. Yeah. So yeah, we use this hidden Markov model, which I just kind of said this, but it assumes that there's kind of these latent unobserved states that are driving the observed brain activity at any given time. And yeah, I think it's kind of a cool way of looking at brain data and taking into account like whole brain collectivation and covariance. So that's what we went with. And then, so getting into like the model selection part. So we tested out different state counts for the hidden Markov model. And then we computed AIC, BIC, log likelihood, and found that we kind of see these like two elbows in the AIC, BIC values. So then we computed cross-validated log likelihood to select a state count of 14. So that's what we went with. But there's a lot more you can do with the model selection stuff, but given that we had limited time, that's what we went with. Yeah, so each state can be kind of defined by the mean network activation across the narrative processing experience. So this is a visualization of the mean activation within each network. And then each network is kind of grouped into families. So we have default mode, salience, executive, sensory motor, language. And you can kind of see the distribution of mean activity levels that characterize each state. So we have like general network suppression in state 12, and this more like higher activity state 11. So this like distribution of activity levels across our states, just to look at that. And then
yeah, and also just kind of very quickly, it's not really human digestible to look at 14 states, but just this is kind of a quick visualization that we made, that we basically just used the same network mass and multiplied in the mean activation, just so that we could actually kind of visually see what's actually going on in these different states in a way that sometimes you can't quite in the just like a vector version of it.
Yeah, and I should also just note, we looked at fractional occupancy and dwell time, which are common kind of state dynamic metrics. So like how sticky is a state, like how much time someone's spending in a state, and then how much someone enters a state over the course of the narrative listening experience. Just to make sure that all states are actually being used. So yeah. You can also visualize the probability of transitioning from one state to another. So we just visualized the transition matrix to see what was going on there. This highest probability is, these are two states that kind of look alike. They're a little bit recurrent in their activity profiles. So higher probability of transitioning from one state that looks very much like another state. So I guess a sanity check that may signal like state splitting or maybe having too many states, that there are these like recurrent ones. But yeah, this is just cool to look at. Yeah.
Yeah, and so basically getting to the event boundary part of it, we can visualize the state path for each subject, and then I'll overlay the LLM derived event boundaries. Obviously, in this view, it looks very messy, but there's some like kind of overall population level structure that you can see in this kind of structure. Like notably, you can see that state 1 during events 1 and 2 at the beginning, that seems to be kind of the dominant state among the population. And then we transition in states 3 and 4. There's a lot of state 9, but it's a little more messy. And then, you know, it gets, and I would say during the kind of rising action of the story, it's very complicated. But we basically then see kind of a dominant pattern in the very like climax of the story. The state, the event like 10 that has a lot of orange inside of it, that's like very much like the core paragraph of the most exciting part of the story, and everyone seems to transition into that state, the same state at that time. And then when it's clear that the like kind of speaker is winding down the story, we start to see everyone switch into kind of having I'm forgetting what state the brown color is, but I think it's state 11. Yeah, something like that, or 10, might be 10. And so yeah, we also have like kind of a second view that might be a little more digestible, where we actually like checked which states are like with false discovery rate corrections, like which states are kind of like dominating each of the events, so we can kind of see the same pattern that I just described actually like statistically validated.
And yeah, this next thing didn't work out too well, but we tested between the binary yes, no, is there a brain state transition and is there an event transition? We did cross correlation with different delays to see if there was any correlation between the overall architecture of someone's state transition going on and their event boundary going on, and there was not. So then I followed up and did kind of like an event lock version of that, where I looked at the proportion, observed minus null of subjects that had state transitions that fell on a certain event boundary. And we see this like one that was maybe significantly, a subject has a brain state transition that aligns with the event boundary, but yeah, overall, not great.
Yeah, and so then we also wanted to check away from the HMM, just kind of, you know, let's make sure that it's not just the HMM fitting in particular way. So we also checked RSA. This is an average across subjects. You can kind of see some structuring. Basically what you're looking for is squares in the RSA, like high likelihood, that line up with the squares created by the grid of the event boundaries. It's not too obvious at the average across all subjects level. And that part of that is because some subjects it fits relatively poorly for. But then you can see for other subjects that there can be relatively good fits, where if you look at this in detail, basically most event boundaries line up with pretty clear squares or groups of sets of squares, which is honestly a lot better than I expected it to line up. So yeah.
Thank you.
Great. Open tail kind of deck. Do the same. And on deck is functional connectivity too.
You log into Zoom and share.
You're right. Should share my device.
Yeah.
Or-
Well, sure what you want to show.
Okay.
Right.
Okay, so we're almost done. Hang in there. I'm Erital. I study chronic pain and emotional therapy. And today I'll be talking about diffusion MRI prediction of developmental stage. We're going to go through the goals, short introduction to diffusion MRI, the methods, my results, and the short summary. So the original goal was to take diffusion MRI data and EEG, correlate them, and predict with that the psychiatric diagnosis. However, this takes about a week to get the data of the psychiatric diagnosis, and I didn't have any time for the EEG. So the new plan, sorry for that, was to get only the diffusion MRI data from the HBN dataset that has MRI and also EEG for the ages of 5 to 22, and predict with that the development stage or the age. My secret goal was just to working with diffusion MRI data, so still worked out. Okay, hope you'll pull through this. So in diffusion MRI, we're taking water molecules and see how they disperse in the brain. So whenever they're all over the place and more random, it will be called isotropic. And whenever they're aligned in the bundles aligning, the water molecules usually go through the tract and not the cross section. So that would be called anisotropic. And one of the methods to quantify that called fractional anisotropy, or FA, which is basically just a proportion of the directional ones with the comparison of the entire molecules. Was that clear? You want me to repeat that? You're good. Okay. What's with the black thingies?
I think it's your Zoom.
You. So we're getting these kind of few bundles, and we are taking the average of them, which is the black dots. And then we're getting the graph to the right, that it's the tract profile. And if you rotate the black dots, you can see that the x-axis in the graph is the node position along the tract, meaning the most left is the 0 node is the bottom one, and the most right, the 100th node is the most top in the bundle. Questions about that? So I used pre-processed data, kindly given to me by Ariel, thank you. And originally I had 2,100 subjects at the age of 5 to 22, but little kids tend to move too much, so I dropped them and just used age 10 and up. I also used quality control score to get out all the less quality data, and I used over 0.5. The histogram goes from 0 to 1, so like the half. There were also 4 different scanning sites in the data set, so I only took the largest one of them. And there are a few subjects with missing data that were also removed. So that left me with 300 subjects, which is still pretty nice, with the age of 10 to 22. So the data is constructed with 24 tract profiles, and I just plotted them to see also a sanity check to see if I'm seeing what I'm thinking that I'm seeing. So there are 5 random tracts and few subjects, and you can see the difference in the different tracts and a lot of similarity between different subjects. Then I used the GLM model to predict the age using 25 regressors. The first one was the sex, and then 24 other profile tracks as we saw. And I took this, you can't see my mouse, but I took the entire profile and averaged it to a one mean number, which is a common thing to do. So here in this data frame, you can see the rows are the subjects. Oh, here's my mouse. The rows are the subjects and each column is a regressor. These are different tracked profiles and one of them is sex. And here is this average number of the entire profile. Moving to the results. First, I wanted to have a presentation of the data and I took all the ages and divided them to 4 age groups. The younger one are 10 to 12 and the oldest one are 19 to 22. You can see that there is a difference between the different groups, but it's not that big. And you can also see that it's not consistent across different tracks. If you would look at the oldest group, the red one, they're not always on top. It's not always the highest FA. So then I took this to a GLM model and these are the results. The x-axis is the actual age and the y-axis is the predicted age. You can see that there is some kind of correlation. It's pretty lame. The R-squared was about 0.26. And when I added regularization like ridge, lasso, and elastic net, which is a combination of the two, I got worse results. So the GLM alone was performed better. So what have I learned? I learned working with diffusion data. I started to befriend GitHub and Jupytex helped with that because it makes everything a little less complicated and it transformed notebooks to .py files. So thank you very much for you two and for all of you for staying awake. More questions?
We're kind of over, so. Thank you. All right, our last but not least group, they're coming up, functional multiple two. There's.
Oh,
you need to
yeah,
share-
I forgot.
Yeah.
Is this? Okay, cool. Hey everyone, I'll try to keep it short and sweet. So the project is fMRI functional connectivity to as the exact same repo, but to as the funky connectivity group. So foreshadowing, I suppose. Originally, we wanted to work with fMRI animal model data to see if physiological and invasive studies that tell us more so about how certain pathways where in single neuronal data draw inferences are usually like later extracted and extrapolated onto like human data. So oh yeah, we're gonna go through the background right now. The original idea was to work with high resolution fMRI data from a mouse model that was a 14 Tesla data compared with human fMRI precision data and see if you could do clustering or dimensionality reduction to see if there were similar networks to group and then train on another data set. So we wanted to use a all-language mouse model data set
So resting state fMRI data, which had control and disease subjects, and we were planning to like later on do a convolutional neural network to see if you can train that model, make it work on humans. That was a little more complicated than what we could have accomplished in this 1 week. But we gave it a good shot. So turned out, all the data sets we found in animals were not processed. So we tried to pre-process them.
Yeah, so our mission idea was to use this resolution data set that contain structural and functional data, and use the structural data as a template and co-register for a structured functional measure. But the problem is that the processing of mice data is a long process, so I tried to apply to pipeline, but guess what? It's take a lot of time, so we have to change completely our data set. So thank you for the funky group to give us the idea and give actually the data set, in particular Chris. So we completely change our data set and work with from the digital quantum project, and we use the most huge population of depression to find some difference between the control and the depression group. And we made also some review about the network that are involved in depression disorder, and we expected to find some difference in this particular network, and we use them like label. And
So we all know what functional connectivity is, but I'll run you through it again. So it's a correlation between both signals. It shows how two regions fluctuate over time, like co-activation. And I was also wondering what other thing you could do with time series. So based on some of the previous projects that I worked on, I thought I'll introduce as well effective connectivity here using Granger causality. So in 1969, Granger released a paper hinting at a statistical model which can predict time series, one time series based on the past time series. So this was the basis of what this Granger causality would be. And it gives you a directional influence of how one brain region can exert causal effects in other brain region. If we go to the next slide.
Right.
Yeah, so the way Granger causality works is we use a vector autoregression model. It takes past values of all regions and predicts the current values. So we have used a lag of 2. So in this case, the repetition time was 0.8 seconds in the MRI data. And we used 2 so that we could take not spontaneous time series data, but we could take 2 seconds, 2 time series data. So we skip 1. So it kind of doesn't reflect the actual hemodynamic response function, but it also isn't so spontaneous. I put it somewhere in between, so it might give you a hint at how these values are being shown. And yes, I'll talk about it in another slide.
Oh, no. Yeah. Okay. Okay, so those are the measures that we looked at the Granger causality and functional connectivity. But what we wanted to do is actually what we wanted to do evolved over time just because of all the constraints we had.
So we decided that we want to use these features and somehow group them together, label them, and we decided we just use the network labels, like because network connectivity, and we decided to use group lasso to find the most predictive features or feature groups of depression. The reason we did with group lasso instead of many other more elaborate maybe algorithms is that originally we were expecting to have so few observations from the mice data, maybe 10 to 20, and we're gonna have maybe hundreds of features, including connectivity data, structural data. Like we had wild ideas, but it didn't come to fruition. So instead, the group lasso is much simpler in scale. In our current data, we had about 200 observations and 200 features. So other algorithms would be also useful. I guess maybe it would be even better. But one other advantage of group lasso is after we get we select the features, we can just look back which ROIs, which labels are more effective, right? So it's for its exploratory way, it's very powerful, I think.
So quickly, like how we ran through the data, we extracted like the functional connectivity and like got a depression score, which was like based on the like stress and depression inventory that the transdiagnostic connectivity project had recorded. So we actually paired mild, moderate, and severe depression all together to be like, oh, that's someone with depression diagnosis, and then 0 for not depression diagnosis. Now, important here, like we had a much smaller subset of people with depression compared to the people without depression, so our data, like further on, looks it's probably a little biased for our modeling.
We can actually move on to the results quickly because we don't have much
Yeah.
time yet. Okay, so okay, so what we did is we first define our feature groups in functional connectivity and Granger's causality. These were different, but we split the data in health training set and a holdout set. Then, as I said, we have imbalance data. So we use stratification to make sure that both our sets have enough representation of depression group and not depression group. And then we did some hyperparameter tuning for group lasso to decide on the strength of regularization. And we trained the final model using the best regularization parameter on the entire training data set, then evaluated on testing data. Okay, so for functional connectivity, we did look at collapse across all the sub networks. So these are some networks, and for instance, the control network has control A, control B. We collapse across all, and we look at all the pairs. Okay, so these are the results. Looking at the functional connectivity, there's the binary classifier. So we have the ROC Ariane curve of 61%, 0.61, which is above chance. And when we look at the confusion matrix, we were successfully classifying depression versus non-depression. And when we look at this selected feature groups, we see that the default is somewhat a moderate network like connectivity between them, and also this default visual network, as well as dorsal attention to limbic system. These connectivities, like across network connectivities, were better, good predictors, and only 3 groups were selected. And what we see here, without any labels, the orange is the depression. The depression group had overall lower connectivity in each of these features as compared to no depression group. So that's the our main finding. And for I think it will skip this one because we did for the Granger causality. When we checked it, the neuroblast was not successful above chance. And we have many reasons why it might be the reason, but I think we're running out of time. So, in conclusion, functional connectivity predicted depression above chance, and maybe what we have done might be just a glorified t-test actually, because when we look at the overall like average connectivity scores, depression group just had lower connectivity as compared to non-depression group. And Granger causality did not produce any reliable predictions. Yeah. Should we put it up here because it's 12 minutes? Okay. Thank you so much. And thank you because it's like here I am and he's still stuck with us. Yeah.
All right, thank you everyone for all those great presentations, and that wraps up NeuroHackademy 2025. Thanks to everyone online.
Reception outside. Yeah. Hope to see you at SFL.
NeuroHackademy 2026.
We'll be here. Thanks so much, people.
Bye, folks.